Welcome to part 2 of GCSE Physics, Chapter 5, Forces and Matter. In part 1 of this series, we explored the most commonly tested concepts in Chapter 5, Forces and Matter of the CAIE curriculum. We looked at past papers from 2020 to 2022 to be able to provide the data behind the most commonly tested concepts for this chapter. We also dove deeper into the concept of Hooke's law. We looked at elastic objects and inelastic objects. We looked at how force and the extension in an elastic object is linked to each other. And all of this was covered in part 1 of the series. In this part of the series, we're going to be looking at the pressure in solids and fluids. If you want to check out part 1 first, then I have left a link in the description for you to do so. So let's dive deeper into pressure now. So pressure is the force acting over a unit of area, right? This is usually how the pressure in solids is described. So if you want to increase the pressure, you either need to have a greater force, or you need to have a smaller area, or you can have a greater force acting on a smaller area. So say you have two people with the same shoe size, but one person is significantly heavier than the other person. So in this case, they would exert a greater pressure on the sole of their feet because they have a greater weight, but they have this weight acting in the same area as the other person. So compared to the other person, the pressure that the heavier person exerts in the sole of their feet is greater. The other way in which you can exert greater pressure is by having a smaller area on which the force acts. Now, if you think about a pin that's used in a bulletin board, it has a very sharp end and that has a very small surface area. So the force acting will act on a very small area, which means that pin is going to exert a great pressure on the surface of the bulletin board. Equally, another way to think about this is, say you were trying to dive into a pool to go deep, versus you were trying to just float on the surface. The way you would orient your surface area will be very different. So when you're trying to dive, you would try to, absolutely minimize your surface area. You might even cannonball yourself in, or you might like dive straight in such a way that, you go hands first and then head next into the pool from the diving board. So what you're trying to do there is you're not spreading the entire body surface when you're trying to get into this when you're trying to get into the pool. And so what you're doing is you are trying to approach it with the shortest area possible. So that allows you to go deeper into the swimming pool. Whereas if you think about when you're trying to float, essentially you try to maximize your surface area, right? You're spreading your entire surface area, and that allows your weight to be spread more evenly, which means you're exerting less pressure on the surface of the water, which means you will float. So although in this scenario, you're just the same person, so your weight is not going to change. It is how you distribute your body surface area to determine whether you float or you sink. And that is essentially pressure or the concepts of pressure and action. Yeah. In fluids, pressure is dependent on the both the density of the fluid as well as the height or the depth from the surface of the fluid. So the deeper you are in the fluid and the denser the fluid, the more the pressure. So for example, if you had a beaker of water and a beaker of mercury and you filled it up to the same height, at any point below the surface of the two fluids, you will find that the pressure is greater in the mercury than it is in the water because the density of mercury is much greater than water. Likewise, if you had a beaker of air and you managed to seal it at the top, you will find that at any given depth in the water, the pressure is greater than it is in the air. So this is something that divers tend to experience on a regular basis because you are at the surface of the earth. There is hundreds of kilometers of atmosphere above you, but it still feels more manageable than when you've dived a few meters deep into the ocean and suddenly you need like a diving suit. So that is testament to the difference in density between water and air. And we also know that in the same fluid, the greater the depth or the greater the height from the surface, you will find that the greater the pressure. Which is why when you're flying in an airplane, you know, we are 13,000 kilometers. I'm just picking a number off the top of my head, but the last flight I flew in, I think I vaguely remember seeing 13,000, not 13,000 kilometers, sorry. That would put you in outer space, but 13 kilometers about the surface, you know, the surface of the ocean. You find that the air pressure is a lot lower, which is why when for some people they go from this region of low air pressure to a region of high air pressure as they land, and the pressure rapidly increases, they find their ears popping, and we've experienced this as well. So the pressure varies with height. That is something that is another concept that we are familiar with, that we've probably experienced when we've flown, especially when the flight is about to land. Excuse me. So to find the pressure in a fluid, it's perhaps more useful to find a formula that links the density of the fluid and the height of the fluid to the pressure, and that is the formula which is rho GH. So rho is this tiny p here, g is the gravitational acceleration, and h is the height within the fluid where we're trying to measure the pressure. And the two formulae, which is the pressure for the solids and the pressure for the fluids, can actually be equated to one another, or you can actually get the pressure in fluids formulae from the pressure in solids. So the way we go about doing this is, firstly, we have to capitalize on the fact that an area is 2 lengths multiplied together, a volume is 3 lengths multiplied together. So mathematically, if you want to get from area to volume, you multiply the area by some length. If you want to get from volume to area, you divide the volume by some length. In this case, because we're trying to equate pressure to essentially the height or the depth, that's the length we're interested in, we want to be able to say that the volume of the fluid divided by its height gives you its area, which again is a rough approximation. This is just us playing around with sort of the mathematical concept of volume and area. Obviously, there are other factors like, you know, what is the exact formula for the area? All of those things tend to come into play a little bit. Is it like a cylindrical area? Is it a conical area? Is it a rectangular area? There's all of these things that come into play. But generally, fundamentally, volume is area multiplied by height. And if you want to get area, that's volume divided by height. So what we do essentially is we plug this new formula for area into the original formula for pressure. So pressure is force divided by area. And we've got pressure is now equal to force divided by volume divided by height. And if we simplify this, essentially because we've got volume divided by height in the denominator, the height then goes to the numerator of the overall fraction and the volume stays in the denominator. So what we've got here is a product of force and height in the numerator, and we've got the volume in the denominator. And then next we capitalize on the fact that the force of a body of fluid is generated by its weight, which is the force of gravity acting on its mass. So the force is equal to the weight, and the weight is equal to the mass multiplied by the gravitational acceleration. So the force is equal to mg. We know that mass is equal to density multiplied by volume. You know, there is a relationship between mass, density, and volume. This is covered in the first chapter of the CAIE curriculum. If we rearrange that equation of density, which is mass by volume, we would get mass as a product of density and volume. We know the density is called rho, so this would be rho v. So force, which is essentially mass multiplied by gravitational acceleration, if we plug in the formulae for mass in terms of density and volume, we would get that force is equal to rho vg, because the rho v is essentially subbing in for the m, right? And now if we take what we've got in terms of force and we plug it into this equation for pressure, so pressure is essentially force multiplied by height divided by volume. What tends to happen is we've got volume in this formula for force, and the force is in the numerator, and we've got volume in the denominator as well. So those volumes cancel out, and that essentially leaves us with rho gh, which is the formulae for the pressure in a fluid. This is something that you will hardly be tested on. This is just to show you that we have not just pulled the formulae for solids and fluids out of thin air, that they are actually interlinked and you can go from one to the other, which is what we've done here. So again, it's just manipulating the fact that a volume is essentially area multiplied by length, which means area would be a volume divided by length. It's just using the fact that the force generated by a body of fluid is because of its weight, which is the product of mass and gravitational acceleration. It also makes use of the fact that the mass of the density multiplied by the volume, and then when you tend to plug the different formulae for each of these quantities into different equations that we've already got, you'd be able to then go from pressure is equal to force divided by area to pressure is equal to rho gh. So it's just essentially just manipulation. But all you need to really know is that in solids, pressure is force divided by area, and in fluids, pressure is rho gh, and again, they are interlinked. So there's a couple formulae related to pressure within fluids that I want to describe here. So firstly, I'll describe the system. So here we've got a beaker. I haven't drawn the nice little curves at the end there. It's got a fluid. It's essentially got two fluids. It's got a fluid A and a fluid B. Fluid A has a density rho A, and it's got a height or depth of HA. So that is going from its meniscus all the way to the meniscus of B. And then fluid B has a density of rho B and a height of HB. And its height essentially goes from its meniscus all the way to the bottom of the container. So we can assume that fluid B is the denser fluid, because if we had two fluids put together, and say they're not soluble in each other, what would tend to happen is you would have two layers of the two fluids with the denser fluid at the bottom and the lighter fluid at the top. So that's what we've got in the system here. And I've just said that if for the case of fluid A, if we just looked at the height from its meniscus all the way to the point of fluid B's meniscus, or the surface essentially, it has a height of HA, which we've shown there. And if you went all the way from the top of both fluids all the way down to the bottom of the beaker, then you've got a height of HA plus HB, which is essentially the heights of the columns of A and the column of B. So that's what we've got there. So the other thing as well that I've got is I've shown essentially an object, and say I've taken two screenshots. Firstly, when the object is at a depth of H1, and secondly, when the object is at a depth of H2. So if I wanted to know the difference in pressure between the 2 points in a fluid, so this is just the object within one fluid, which is fluid A, which has a density of rho A and a total height of HA. If I just wanted to know the difference in pressure between these 2 points, I would try to find the pressure at the bottom point, because it should be higher, and subtract the pressure at the top point from it. So that would be essentially rho A G H2 multiplied by rho A G H1. So because rho A and G will be the same in the fluid, if I take rho A and G out, I would have the difference H2 minus H1. So I've just simplified it to say it could be for any fluid. If I wanted to find the difference in pressure between 2 points within the fluid, it would be a matter of multiplying its density and the gravitational acceleration, which I would take out. In the case of fluid A, obviously it'll be rho AG, but in the case of any generic fluid, it'll be rho G. And then I multiply it by the difference in the depth of the 2 points. So in this case, the first depth is H2, or rather the first depth is H1, the second depth is H2. But because H2 is deeper than H1, you would take the deeper depth and subtract the shallower depth from it. So what you essentially have here is you've got rho G delta H. So delta is a symbol usually given for a difference, and that difference is the difference between the deeper point and the shallower point, i.e. H2 minus H1. So that is how you find the difference in pressure between 2 points in the fluid. The next thing that I want to show is being able to add pressures in two different fluids to be able to find a pressure at any point in them. In this case, I've started off with something slightly easy, where I want to say find the pressure at the bottom of this beaker. So the bottom of this beaker, you're going to have pressure exerted by A, and then you're going to have pressure exerted by B, and they have to be combined together. The pressure exerted by A will be equal to the product of the density of A multiplied by the gravitational acceleration of A. The gravitational acceleration generally. The gravitational acceleration is going to be the same for A and B because they're both near the surface of the Earth. And then HA is the depth of fluid A. In the case of fluid B, it's going to be the same. It's going to be the product of rho B, which is the density of B, multiplied by the gravitational acceleration G, multiplied by HB, which is the depth of fluid B. And if I added those together and took what was common, G is the only one that's common between the two fluids because, again, it's constant near the surface of the Earth. And that gives me with G multiplied by rho AHA, that is the depth of A multiplied by its density, plus rho BHB, which is the density of B multiplied by its depth. So we've just got that there, and that is how you would find the pressure at a point below two fluids. Sometimes what they will do is they will provide you with the atmospheric pressure. So say instead of having one of these fluids here, the fluid that you have is the atmosphere. So say fluid A was the atmosphere, so they will just give you the atmospheric pressure, which is roughly around 1 to 10 to the power 5 pascals, so around 10,000 pascals. That is the atmospheric pressure, slightly more than that. And they would ask you to find the pressure at a certain point, or the total pressure at a certain point within the fluid, and you just have like fluid B essentially. So when you're given such a question, it's important obviously to add the atmospheric pressure to the pressure that you calculate within B itself, right? Because obviously you would have rho B, you would have HB, which is the depth within B, and you would have obviously the gravitational acceleration. But you should not forget to add the atmospheric pressure to that value to be able to get the total pressure underneath the fluid surface. But sometimes you would have scenarios where instead of the atmospheric pressure, they would give you another fluid. Maybe they would give you another fluid and you would also have the atmosphere. I think the key thing to keep in mind is that if you want to find the pressure at any given point, just remember that if it's within a fluid or within two or underneath two fluids, you would have to obviously calculate the pressure at the depth for each fluid. And if they're also giving you atmospheric pressure, just don't forget to add that value in as well, because the atmosphere is exerting a pressure as well. Usually the thing is when you're looking at different objects on the surface of the Earth, because we know that the atmospheric pressure exists everywhere, we tend to assume that, you know, it's just there. We don't tend to usually include it. And that's a bit like, you know, do fish really know that they're in water? Do you know, would they really grasp the concept of water really? It's a bit like that. But the thing is, when in a question they explicitly, when in a question they explicitly give you the value of the atmospheric pressure, it's more often because they want you to use that. So I think that's going to be your clue, which is why I've given you this as well, because, you know, this is a more elaborate way of doing it. But essentially, if they've given you the atmospheric pressure, you've only got one of the fluid, they've given you this value here, rho AGHA, as bulk value, and you just need to be able to add that to this value that you calculate to be able to get the total pressure at the point below fluid B. So hopefully that made sense. I appreciate that there's a lot of formulae which is involved, but in a nutshell, we just wanted to show here that you can go from the formula for pressure in solids to the formula for pressure in fluids in a rather straightforward manner. And I've just shown the derivation here. Ideally, you just need to remember these two formula. And then in this page, I've shown how to calculate the difference in pressure between 2 points in a fluid for a generic fluid. I've just shown it by describing essentially 2 screenshots within fluid A. And then I've also shown how you calculate the pressure at a point below two fluids. So I've taken here fluid A and fluid B, each with different densities and different depths. And we've also seen that sometimes you would have just the atmospheric pressure provided. So you can assume that the atmosphere replaces fluid A, and instead of giving you the density of the atmosphere and its height, they would give you just a value of the pressure it exerts. And you just have to add that to the pressure value that you calculate for your fluid, given its density and the depth of the object, or the point where you are interested in the pressure, and just add it to the atmospheric pressure to get the total pressure. Remember as well that you only do this when the atmospheric pressure is given. If the atmospheric pressure is not specifically given, you just have to calculate this bit here, which is, PB, or rather rho B G HB, which is the density of that fluid there, multiplied by the gravitational acceleration, multiplied by the depth at the point where you're interested in finding the pressure within that fluid. So hopefully all of this made sense. If you found this useful, please consider liking, sharing, and subscribing. And also let your friends know about this channel if you think they will benefit from the content for it. I will be creating videos on applying both the concepts of pressure as well as Hooke's law to past paper questions, and we'll link them in the description for the videos. Thank you for your time. Bye-bye.